I will begin. I'm wasting precious class time with nonsense. I'm sorry. Dear Father, we thank you for this day. I thank you for these students. Just ask you to just guide our thoughts today, Lord. In your name I pray. Amen. Okay, so tensors. Let me show you a calculation or two about tensors. And so these examples come to you from Dummett and Foote, section 10.3, I think. And so I'm just going to do a couple simple examples just to try to sort of dip our feet in the pond here. So example 1, we'll start small. This is on page 368. And here we got an R module M and R module N. We're looking at the tensor product over R of these things. And here's the calculation. M tensor 0 is M tensor 0 plus 0 is M tensor 0 plus M tensor 0. And so therefore what? What can we say about M tensor 0? It equals 0, right? So the tensor product of something with 0 is 0. So the tensor product is going to be some sort of formalization of like abstract multiplication. I think this is comforting. 0 times something ought to be 0, right? Yeah. Likewise, you can show that 0 times n by essentially the same argument. Example 2, if we're looking at z mod 2z tensored over z with z mod 3z, so like watch and learn. Dr. Smith is at peace with my board work. Watch me offend Dr. Smith. No! So he does not like this notation. For he is a number theorist, and it has a different meaning for them in terms of p-adics. But anyway, for me, I use Z2 and Z3 to mean those, right? Anyway, so of course, in Z2, we have 3a is equal to a. I think we could all agree with that in Z2, right? And so we're going to do a little calculation right here. A tensor B, all right? A tensor B is equal to 3a tensor B, all right? Which is what? What did we learn about one of the fundamental properties of the tensor product is we can move ring multiples from one entry to the other, right? So 3 is in Z. We can move 3 from here over to there. So this is by construction of the tensor product, A tensor 3B. But what is 3B? It's 0, right? Because we're where? We're in Z mod 3. So 3 times anything in there is 0. So this is A tensor 0, which is, by example 1, what? 0. What? So any simple tensor. By the way, what's a simple tensor? It has the form V tensor W. So for some V and W. All right. In contrast, if we had like, V1 tensor W1 plus 3 times V2 tensor W2, this one is not simple. A simple tensor can be written as the tensor product of just one thing with another thing. No addition. Yeah.
Does that say V1W or is that V comma? For some
V comma W. Yeah. I mean, I guess in my current context, I guess V would be, well, I don't know what my current context is with this. In M tensor N, I guess V would be an M and W would be an N, right? So a simple tensor is just the tensor product of one thing from the first module with one thing from the other module. But the tensor product is itself in our module, so we can add together elements, right? So there's not just simple tensors, there's things like that. Actually, it remains to be seen. In a given tensor product, are there tensors which are simple and other ones which are not? I mean, that's one of the questions you can ask about a tensor product of two modules, is do there exist more than just simple tensors? Can you always reduce a sum of simple tensors to just one tensor, right? Like this, I said it's not simple, but actually I don't know in the abstract. If there existed, say an A and B, such that this is A tensor B, you know, if I could somehow rewrite this according to the rules of the module, which I haven't stated, as the tensor product of a single element with another one, then that would in fact be a simple tensor. It could be reduced to a simple tensor. All right? I'll take it. I mean, I missed, but anyway. Okay, so, but this is an arbitrary simple tensor, right? So if you take a sum of these things, it's still going to be 0, right? So if you can show an arbitrary simple tensor is 0, then it shows that the whole thing is 0, right? This shows that, in fact, Z2 tensor over the Z3 is what? It's just 0. But remember, there's a connection between the tensor product of modules and maps. All right, so there's something actually kind of interesting that comes from this. He says it follows that there does not exist a bilinear map from Z2 cross Z3 to G, where this is any abelian group. Remember, corollary 12 says that there's a one-to-one correspondence between R module homomorphisms from M tensor n into L and bilinear maps from, I'll write it up here. So here was the, I'll just remind you again, R bilinear maps, say from M cross N into L, correspond to R module homomorphisms phi going from M tensor N into L, right? And they satisfy this commutative diagram. We got the iota. So here's the So, I mean, I said there does not exist I should say does not exist a non-trivial bilinear map, right? See why that is? Does that make sense? Why that's true? So if you think about M being Z2, N being Z3, R being Z, right? Then this tensor product space we just showed is 0. So what maps can you define on 0? Just the 0 map, right? It's single valued. So you map 0 to 0, that's it. So there's a direct correspondence between these and those, though, right? So if I show this is 0, it says that there is no non-trivial bilinear map. Now, of course, if you just went and tried to find directly a bilinear map on Z2 cross Z3, you know, that would You could also show that it's 0 through direct arguments, but I think this is kind of a one neat application of the tensor idea. Is it gives you insight into bilinear maps in this sense. So you might wonder, is like Zm tensor Zn always 0? Right? What about, I mean, we did 2 and 3. What if you did another example? Let's see here. Actually, it's the same example continued in his. He looks at like Z2 tensor Z2. What is this? What's the deal with this? Like, what can you describe what this tensor product looks like? Well, so simple tensors would be what? We've got 1 tensor 0, we've got 0 tensor 1, we've got 1 tensor 1. Anything else? Oh, how about 0 tensor 0, right? So we know from example 1 that this is 0, that's 0. These are all the 0 in the tensor product of Z2 and Z2, right? And so our only hope is that is this non-zero? And how does he argue that that's non-zero? How do you think Dummett and Foote argues? I don't know which one it was. Was it Dummett or was it Foote who made this argument? Your guess is as good as mine. So we exploit the other direction of this arrow. We exhibit a non-trivial R bilinear map. See, if there exists a non-trivial R bilinear map over here, that means that this can't be the 0 tensor product, right? And what's a good bilinear map on Z2 cross Z2? So look at Z2 cross Z2 to, I don't know, Z2. That's an abelian group. And we want to define some mapping, let's say T. How about this? T of A comma B equals 2. Well, what he does is AB. You can easily verify that that is a bilinear map. It's linear in the first slot, it's linear in the second slot, and it's non-trivial. Right? You can check. Plug in 0, 1, what do you get? Oh, that's a bad choice. Plug in 1, 0, oh, another bad choice. Plug in 0, 0, oh, also a bad choice. But if we plug in 1, 1, what we get? T of 1, 1 is 1 times 1, which is 1, so therefore it's not the 0 map. So there exists a non-trivial Z2 bilinear map, hence the set of, therefore we can't, therefore M tensor N, in this case Z2 tensor Z2, can't just be 0, and there you have it. That is a very kind of sneaky, indirect way of arguing that this is non-zero, but there it is. And so what do we have? This basically has 2 things in it. What does it have? It has 0, and it has 1 tensor 1. So what is Z2 tensor Z2 up the isomorphism of rings? It's Z2, right? This is isomorphic to Z2. Which kind of makes sense, right? If you multiply Z2 by Z2, you just get Z2 again, right? Admittedly, this is the tensor product, so it's an abstraction of just plain multiplication, but it's kind of intuitive. Maybe it's not intuitive that Z2 tensor Z3 is 0, though, right? Maybe you'd think it would be Z6, but it's not. That's not how it works, yeah. Or Z5.
So Z2 tensor Z2 is isomorphic to Z2 as a ring?
Yeah.
Okay.
Mm-hmm.
So
Yeah.
So then here we're taking the tensor. We just established
These.
that basically no matter how you tensor, you're going to be working with the only elements you can work with is 0 and 1 tensor 1, and 1 tensor 1 will always act like the 1 will.
Yeah, well, if we add 1 tensor 1 to 1 tensor 1, we get 0. if we multiply one tensor 1 times one tensor 1, we get one tensor 1, yeah.
How would that work? Would that be like a, so I'm wondering how the transformation fits in here. Is the transformation that we use just evidence?
It's just, yeah, I mean, I was just,
Evidence that it's non-zero?
right, this is just to argue that, there exists non-trivial bilinear map, which then, of course, shows that this is not all zeros, and that these bijectively correspond by the corollary, therefore this can't just be 0. Otherwise it would violate the bijection, yeah.
So if you did like one tensor one, and then if you're multiplying them, is it doing the tensor of those things again, or is it something else, like actually multiplying them?
I'm glad you asked that. That's the next section that I'm going to talk about. So we'll get there. So your question is, how can you take the tensor product, can you multiply two tensor products together? And yes, you can. There's something called the Tensor Algebra, which allows us to take tensor products and multiply them together in some kind of bigger thing. But all right, let me actually try to get to that. I want one more maybe like two more comments here, then I'm going to go ahead. So generally, just to kind of finish the story here, if you look at Z mod mz, tensor over Z of Z mod nz, what you get is that it's isomorphic to Z mod GCD of M and N. Z. So like the GCD of 2 and 2 is 2, the GCD of 2 and 3 is 1, Z mod Z is just the 0 space again. So for example, if we were to look at Z4 tensor, Z6, that would be up to isomorphism Z what? Z2? Yeah. So you'd be able to show in Z4 tensor Z6 that most everything is 0 except for like one thing, which I think is 1 tensor 1. It could be wrong. Yeah. But anyway, I'm just using that. Now, he has more examples here. Example 4, he shows that if we look at Q mod the integers, and we take the tensor product of that over the integers of itself, like that, then that's actually equal to 0. And the calculations, I can go through the calculation. I'll do that actually. So we go A over B mod Z, tensor with C over D mod C. He's using this notation for equivalence classes of integers, or for rational numbers mod the integers. Yeah.
From the example above that, the Z4 tensor Z6, is there only going to be one thing that's non-zero, or like could 1 and 5 both be non-zero, or something like that?
If we believe what's written, there will be a way of taking those two non-zero things and seeing that they're equal. What are your two non-zero things that you came up with?
Well, I didn't really come up with any. I was just wondering if it like 1 and 5 or something like that.
I suspect like 1 tensor 1 is non-zero in here. And I could do like, I don't know, I feel like maybe that's equal to, say, 5 tensor 1. That would well, but that's just literally the same. But the thing is that that's also 5 times 1 tensor 1. So that would be equal to 1 tensor 5. I can move integers from one to the other over the tensor, the z tensor. So that freedom allows you to get from 1, 1, 1 to, I could add 8 to it, right? That would bring in 9. So 9 tensor 1, which would be, 1 tensor 9, but z6, that's 1 tensor 3. A lot of things that look like they're different on the surface are going to be the same in the tensor product of z4 and z6. Again, the governing rules is just we have those 3 properties that we quotiented by, right, that set up the tensor product. One of those being that we can move ring multiples from one to the other. And then the distributive properties. And of course, it's an abelian. At the base of it all, it's a quotient of an abelian ring, right? So we still have like additive. We can add simple tensors, and that addition is commutative and associative. So what's he do here? Check this out. So I'm going to do it. So what if we put a d in here and multiply it out there? You could do that, right? And then this would give you a over bd. My usual notation, guys, would be plus z, I don't know, this is mod z stuff, but whatever. I do plus z. It's a quotient mod z, right? So there you go, plus z. And we bring the d over, we get c plus z. Because when I move the d into the second slot, it cancels the d. Game over. This is 0. Because we can absorb c as an integer. It gets sucked into the integers. That's the coset, the 0 coset. So then 0 tensor times 0 is 0 again, example 1. So we've just shown that an arbitrary thing in that tensor is 0. And then finally, well, he also, he has a few more examples. I'll let you read them. I think that's good for us in here at the moment. Now, again, I'd like you to read this section just to make sure you appreciate what else we know about tensor products, in particular, that we can take the tensor product of homomorphisms. It's like if you have 2 linear transformations, for example, you can take the tensor product of the linear transformations. That's a thing, all right? It's a new linear transformation on some larger space. The tensor product is associative. If you have 3 modules, like m tensor n tensor q would be the same as m tensor n tensor q. That's theorem 14, although he has L instead of q. Then towards the end of the section, he introduces a multilinear map. We talked about bilinear. Multilinear just means, well, multilinear, more. You talk about multilinear maps, and he then has corollary 16, which shows this. There's a similar bijection between our multilinear maps and our module homomorphisms from not just 2, but like a finite collection of modules tensored together. So it would be something like M1 cross M2 cross MK to L versus the phi over here would be from, say, M1 tensor M2 tensor tensor MK into L. And I think what K linear here means is that it's linear in each entry, right? And there's still this unique correspondence, right? That's corollary 16. There's always a connection between the tensor product and multilinear maps in this way. That's what the corollary says. Now, so then I'll just write these up on the board here. So one or two, and then I'll change gears a bit. So theorem 17, it tells us if we have the direct sum of two modules like M and M prime, and we take the tensor product over the ring, for which there are modules, over N, right? Then there is a unique group homomorphism. And what do you think this is going to be isomorphic to? Indeed. It is exactly that. So the internal direct product or the external direct product, depending on what your context is, and the tensor product behave in the natural distributive sense, just like you'd like. Yeah.
Is there a reason that the R is on the tensor product on the top one, but the direct sum on the bottom?
You know, fine, R is all around. R. I think they're optional everywhere, really. But corollary 18 is exciting. Actually, corollary 18 is a shout out to the first 4 pages in this section, which I completely skipped. I mean, this is the essential import, which is that if you have R subring of S, then if we take S, I mean, that's probably a little bit of an overstatement, but roughly speaking, this is what the first part of the section is about. If we take the R tensor of so Rn is R cross R cross R cross R n-fold times, right? The Cartesian product of n. Then this is up to isomorphism, just Sn. To give you some more just direct applications of that. If I take the complex numbers and I tensor product with Rn, that is up to isomorphism Cn. That's what that final corollary says. In other words, tensor product is a way of swapping out the scalars you have, maybe for a bigger set of scalars. Right? Rn has real scalars. We take tensor with C, we get complex scalars. But the same sort of space, right? They're still spanned by the standard basis E1, E2, En. Yeah. Mm-hmm.
What would R for the tensor? What subscript would you put on the tensor?
Oh, this one. That is a good question. This should be over the reals. This is a real tensor. Yeah.
Oh, okay. So
Thank
it's
you.
always over the subring, or yeah, that's my question. Always over the.
I don't. Yes, that's a good question. I don't think that actually be a decent test question in here, right? Like, could I replace that R with C? Why or why not? You guys tell me. Would that even be allowed? Could I reasonably write C tensor C Rn? Well, forget about C, just whatever. Is that even meaningful? True, possible, false.
You can still multiply things in Rn by things from complex numbers.
Could we? What if it's R3? How do you multiply something in R3 by the complex numbers?
I just think every element by the same complex number. Like so you get x, y, z in Rn.
But I don't think that would give, I don't think that gives Rn a C module structure. See, that's the trouble is we don't have a way to multiply complex numbers on Rn. That's the problem. To take the tensor product of M and N, we need M and M to be R modules. See, if I put the complex numbers are a C module, sure, but Rn would only be a C module if we're lucky. I think if you had even n, then you could identify Rn with Cn over 2, and then you have a C module structure from that. Like R2 can be viewed as a C module just by thinking of R2 as the complex numbers. I don't know if I can put a C module structure on R3. If we could, then we'd be in business. So the question really reduces to, can we view Rn as a C module? Is that possible or not? I'm tempted to say no for odd dimensions, but I don't know if I have a proof of that. It would have to be like a stupid module structure, like it's just 0 or something. Is that allowed? I don't know, but yeah. For odd n. For n. Oh, okay.
Okay. Another question then.
Mm-hmm.
You could then, that could be a cube. You could quotient tensor. Like, they're both quotient modules. Right?
Oh, yes, yes. We could both. Yeah, sure enough, yeah. We could put a Q there. Yeah, yeah. In fact, I think the last example in this section explores exactly that kind of different choice of tensoring with respect to looking at the tensor product of C with itself. There's like 4 different tensor products that would be meaningful there, or something like that. So that's like the last example in this section. But another example he gives right after this is if like you took Rm and you tensored it with Rn over the R. What do you think that is? If I take Rm, tensor Rn over R, the R tensor, which would that be up to isomorphism? Rmn. Yeah, that's exactly what you get. So I think I told you just enough to be dangerous. And so look at the homework problems I've assigned you, see if you can work them. I think you probably can with what we said. So I'm actually skipping ahead a bit. So technically, the next section in Dummett and Foote is on exact sequences, all right? Which is, well, the next section is actually on what's known as homology or cohomology, which is, well, I'll get back to that. So what I'm doing is I'm skipping ahead and I'm talking about a little bit, just a little bit, about symmetric and antisymmetric tensors. All right? So, ooh, stink, I shouldn't have done that. I actually wanted what I just erased. Oh well. Ow. So, oh, why? You'd think I'd know by now not to breathe after I spray. So I'm actually skipping ahead to the other place where tensor products are discussed, which is the end of chapter 11. The start of chapter 11 is linear algebra. You have had 321, so good. We will do some more linear algebra in here shortly, but at the moment, I just want to talk about a couple definitions, and so the first of which is a multilinear. So if we have phi is a mapping from V1 cross V2 cross Vn to W multilinear. Then that means that it's linear in each entry, all right? This is on page 435. This is section 11.4. Now, he says this is called, it's called R multilinear if it's an R module homomorphism for each entry. And it's also known as an N multilinear function on V. If, and actually I'm not interested in this so much. I'm interested in the case that all of these V's are the same V. All right, so if we just erase that and go V, 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 n-fold times, right? Then this is N multilinear on V. So if we look at an N multilinear map on V, there are two very special kinds of, this is N multilinear map on V if W is equal to the reals or the field over which we're talking about. So here, oh, good grief. R, V is an R module. Sorry, I have to shake loose my vector space prejudices. So if the output is the ring, then it's known as an N multilinear form on V. All right. So, in fact, N multilinear forms on V are very interesting. And there's two especially interesting kinds. The completely antisymmetric and the completely symmetric. So let me start with completely symmetric. A completely symmetric multilinear form. If we had this, if phi of, say, x1, x2, xn is equal to phi of x of, let's say, sigma 1, x of sigma 2, x of sigma n, where sigma is an element of Sn, right? In other words, it's a permutation. So if the N multilinear form is such that it doesn't matter how you shuffle the inputs, it doesn't change the output, then it's said to be completely symmetric. So if we're talking about a bilinear form, this is very simple. In the bilinear case, we're just talking about phi of x1, x2 equal to phi of x2, x1. I mean, that's it for the bilinear case. Okay? Then you can also talk about, this is completely symmetric. Symmetric and linear form. The completely antisymmetric, or just antisymmetric, antisymmetric and linear form has phi of x1, x2, xn equal to the sine of sigma times phi of x of sigma 1, x of sigma 2, x of sigma n, where again sigma is a permutation. Now the sine of sigma, this is 1 if sigma even. This is minus 1 if sigma is an odd permutation. So in the case of a bilinear form, there's just one thing to say. An antisymmetric form has what? We'd have phi of x1, x2 equal to minus phi of x2, x1, and that's it. Right? tensor algebra. Well, I guess I should give you one definition. Definition, determinant on V n-fold times, all right, going to the ring. And here I'm supposing that the, oh goodness, he's got some, I'm not sure I'm giving you the full generality of the definition that he has in here. Shnikes. If you'll allow me to fall from grace here momentarily, let's just suppose that the dimension of V is equal to n. In other words, it's a free, let's suppose that it's a free R module. What is it?
I did want to ask this, but I can't figure it out. Sigma, what does it mean if sigma is even versus is odd? Why for n equals 2 is x1, x2, is phi of x1, x2 equal to negative phi of x2?
Because sigma in cycle notation is 1, 2, and it's just a single transposition, which is odd. There's just one of them. It's, remember, odd and even is the number of transpositions in the disjoint cycle. Well, the cycle representation of the permutation.
So then, say n was equal to 3.
Mm-hmm.
Would you have multiple options for which sigma you're using? You could do 1, 2, 3, or 1, 3, 2.
Oh yeah, yeah, and
It would always be positive.
there are 6 interesting cases in n equals 3.
Because you can still have 1, 2, and
Yeah.
1, 3, and you could, okay.
Starting with 1, 2, 3, you can do 3, 1, 2. 2, 3, 1. And then, of course, there's the 3, 2, 1, 2, 1, 3, 1, 3, 2. These are odd permutations, and they give minus for the sign. Those correspond to the pluses and minuses we see in the cross product formula. So this one here, so supposing V is n-dimensional as a R module at least, all right? So as a free, suppose it is free rank n, all right? Then I think in that context I can define determinant to be the unique, all right? It's going to be the unique antisymmetric n-linear functional, right? It's the unique antisymmetric n-linear functional such that it takes the determinant of E1, E2, E3, En to just be 1. So determinant, on the other hand, of course, is you could also think about the determinant and going from like good grief, Rn by n to R, with the understanding that what we're doing is we're looking determinant as a n multilinear map on the columns of the matrix. So this is just like a kind of twisted way of saying the determinant is the unique n multilinear map that sends the identity matrix to 1 and is completely antisymmetric if you swap any 2 columns. So getting back to what Bethany was asking me about a little bit ago, we can in fact define the tensor product. So Tk of m is m tensor tensor m, k-fold times. And then the tensor algebra on M is the direct sum, say k equals 0 to infinity, of tkm. So this has in it, at the 0th order, we understand there is the ring. Like k equals to 0 is the ring itself. Okay? K equals to 1 is the module. K equals to 2 is the tensor product of the module with itself. This is k equals to 2. K equals to 1. K equals to 0. And so forth. So in this so-called tensor algebra, which is an R algebra, in the sense which is defined earlier in the chapter 10. In this tensor algebra, you could take those tensors we were talking about earlier, and you could multiply them together, right? And you could go from something that's built from like a tensor product of two things. If you take two things and put them together, you got how many things? You got 4 things, right? So you'd go from like k equals 2 with k equals 2, you tensor those together, that gives you something in k equals to 4. So there's a z grading by the number of tensor products appearing in the object that you're looking at. So this is the tensor algebra. You'd say, okay, so what? Well, from the tensor algebra, we can build 2 very special things. We can take the tensor algebra and we can quotient by the following. We can quotient by m1 tensor m2 minus m2 tensor m1, the ideal generated by that, okay? So look at all the ideal in the tensor algebra generated by the difference of these simple tensors. So what does that do? That quotient is the quotient in which we can just commute the tensor products, right? This is called the symmetric. This is the completely symmetric tensor algebra, SM. But you could also take the tensor algebra and quotient by the ideal generated by just M and M. In other words, say that when it's repeated, that's 0. That, hey, curses. No, that's it. So this definition I'm quoting is on page 446. The one I'm writing at the moment, this is on 446. The symmetric one is actually on page 444. These are both in section 11.5. Yes, Bethany?
So for the first one, the things that do commute are 0? Is that what you said?
Well, since we're quotienting by that, that means that in this space, the tensor, you can commute tensor products. In this space, if we have the tensor product of anything with itself, it's 0. So long story short, this actually you can look at is built from things like A, and here's the notation I've seen, not in Dummett and Foote, but other places, like A circle B. This is the so-called symmetric tensor product. So that's something like 1/2 A tensor B plus B tensor A. If you build this from that, you can easily see that A circle dot B is equal to B circle dot A. That's like a fundamental 2 tensor. Down here, these are the wedge products. So down here, you'd have something like A wedge B, which, that half, I don't think that half is there. Sorry, guys. Which, it's a question of what's the word I'm looking for? Convention. Whether or not that half is there. It's a combinatorial choice of the book. But A wedge B would be like A tensor B minus B tensor A. You see what that does? That has like A wedge A is what? It's 0. Anyway, it turns out that we can use the wedge product as a nice notation for the things in the antisymmetric tensors. We can use the circle dot for things in the symmetric tensors. I'll just tell you the long story short of it. I don't want to belabor this point. I could talk about these things for weeks, but that's not what this course is about. I'm just trying to give you just pure survey mode at the moment, except for your homework. But sorry. Essentially, if we're looking at a commutative ring, I think this is more or less just polynomials. They can get as big as you want. You can commute the order of things. So it's just like sort of multilinear polynomials is essentially what this behaves like. On the other hand, the wedge product, if we're working over a finite dimensional space, the highest thing you can have is the n form. Past that, it's automatically 0. So this is actually finite dimensional. If we're in a finite dimensional vector space, this is what's called the exterior algebra. These things I talk about at the end of Calculus 3 if I'm left to my own devices. And you know what? I think what I'll do is I'll make a video. I'm going to actually send you guys a link to that video for Friday. All right? So what I was trying to get to is actually there's also this universal property between antisymmetric multilinear forms and our modular homomorphisms from the antisymmetric algebra. There's also a universal property from our modular homomorphisms from the symmetric algebra and completely symmetric multilinear maps. So like there's this beautiful interplay between these objects and those objects. But listen, I don't want to overwhelm you guys with like actually learning all of that. I'm just trying to like alert you to some of the structure. I hope I've said enough that you can do the homework problems. If I haven't, let me know. I'll try to scale it back or something. I need to take a look at the homework again, but I think that's about all I have time to say in here for this. Oh, I'm sorry, I'm way over. I can't be here Friday, unfortunately, and I was hoping that I would get Dr. Sprano to sub in, but he can't. So it leaves me with a question: is are you interested in seeing more about symmetric and antisymmetric? I have some pretty good Calculus 3 lectures where I actually talk about the the wedge product just in R3. So it's much more like concrete. You can see how it works with Calculus 3. Are you interested?
Yeah. Didn't you talk about this at the end of linear? Or like, you just had something on it.
Maybe briefly. I tell you, I'm gonna send you guys a link to that, and then we'll just we'll try to skip. No, I can't skip. I was gonna say we'll try to skip the. I guess I'll just have to pick up with. I'll try to give a really brief treatment of section 10. Where was I? 10.5. So coming back Monday, I'm hoping to show you a honest to goodness Z module which describes something about the geometry of space.
Like outer space?
Inner space. I don't know. You can hit it.